Okay, good morning, everybody. Today we're going to continue talking about energy, and we're going to talk about energy flowing from one form to another. We're going to talk about energy in systems of more than one object and more than one interacting object. So that's our goal. So here's what we did last time. So last time we introduced the energy principle, which tells us that once we've chosen a system, and the idea of system and surroundings is really, really key when we're talking about energy. Once we've chosen a system, that the change in energy of that system has to be caused by inputs from the surroundings. And we got our first way of calculating inputs from the surroundings, which is mechanical work, a force applied through a distance. And that distance, that displacement, is the displacement of the point at which the force is applied. And it's going to turn out that that's important. The thing that actually is changed by energy inputs, so far we've only taken systems of one object, which we've modeled talked about as a particle. And what it means in this case to be a particle is that it either can be very tiny, but the basic idea is there's no internal energy in a particle. It can't vibrate or get hot or anything. So it's just a particle. You can think of electrons as the ultimate particle, if you like. They really are. And the energy of a particle is equal to gamma mc squared, where gamma is our friend 1 over the square root of 1 minus v over c quantity squared. And we could divide it into two pieces. The mc squared part was called the rest energy, and that's the energy that an object has even when it's at rest, just due to having mass. And the kinetic energy, the extra energy that it has because it's in motion. And to calculate kinetic energy for a particle, the most general thing is to take gamma mc squared minus mc squared. However, for something going much slower than the speed of light, that's not effective. And so we came up with an approximate expression for kinetic energy at low speeds, which is a half mv squared. We also saw that we did some calculations and looked at some examples and saw that work can be either positive or negative, and that means that this corresponds to this piece of the energy principle here. Work is positive. Positive work increases the energy of a system, and negative work decreases the energy of a system. So energy flows into a system if work done on it is positive, flows out of a system if work done on it is negative. And the sign of work depended on the relative directions of the force applied and the displacement being the thing we've written as delta R. This is the displacement of the point at which the force is applied. So if the force is in the same direction as the displacement, work is positive. If the force is opposite to the displacement, work is negative. You're maybe slowing something down. If the force is perpendicular to the displacement, then by our definition of work, you have done no work. Even if it feels like you pushed hard on something, the energy, you haven't changed the energy of the system. And also if it acts through zero displacement, even if you apply a force, but the thing doesn't, the point at which you apply a force doesn't move, then the work done is actually zero. Now, what do you need to know of all this? What you need to know is this, and by know I mean memorize. So you need to know the energy principle, just like you need to know the momentum principle. And to make sense of the energy principle, you need to know the definition of particle energy and the definition of how to calculate work. So those are things you need to have memorized and be on top of. Okay, So I'm going to do things a little bit differently for a while, because I think that it's been difficult for you to just concentrate enough to stay plugged in during an entire lecture. So I'm going to take a little more time to work examples and have you work on things, which means that there's a few things we just won't cover in a lecture and you'll be responsible for reading about. And I'll tell you what those are when we move along. So let's start out with a question to see if we can apply what we learned last time. So suppose that there's a cart with a fan mounted on it, and when the fan is like a propeller, so when the fan turns, the air exerts a force on the cart plus the fan to speed it up or slow it down. We have a cart with a fan on it, the fan is on, and the force on the cart by the air is in the minus x direction, and the fan cart is moving in the minus x direction. So during the interval from which the fan cart has this displacement, shown by delta r here, is the work done by the air on the fan cart positive, negative, or zero? So here's what you said. 77% said that the work done was positive, which is correct. And some of you, about 20%, said that the work was negative, which is not correct. So let's see how that comes about. Let's just review that before we go on. Note that we already did explore this, that work comes out to greater than zero if the force is in the same direction as the displacement. And so it doesn't have anything to do with whether the force is in the negative x direction or the displacement's in the negative x direction or anything. It's really the relative direction. And so we have fx work is equal to fx delta x plus fy delta y plus fz delta z. These are zero. And here, fx is a negative number. Let's say it's f is negative 300 newtons. And when delta r is in the negative x direction, it means it's getting more negative. So let's say it goes from negative 3 meters to negative 5 meters. Then delta x is going to be negative 5 minus a minus negative 3 is going to be a negative 2 meters. So we'd have something like negative 3 newtons times negative 2 meters, which gives us a plus 6 Newton meters. Okay, so if you're not sure, make up some numbers, because that's how you can tell. Are there questions about this before we go on? Now, an interesting corollary of this is that suppose you crouch down, you're standing up on the floor, you crouch down, and then you jump up so that you're going up in the air. So how much work, so there was a force applied at you, you're the system. So the system is you. The surroundings, well, the earth is pulling down on you and the floor is pushing up on you. since your momentum changed in the plus y direction, it must be that the net force acting on you was, so we have a delta P upward, so therefore F net was also upward. But how much, and that must have been due to the force by the floor, right? So the floor exerted a force up, the Earth exerted a gravitational force down, but the force by the floor was larger. How much work did that force do between the time, so that's where you're going to end up, but let's draw an intermediate picture here. So here's the time when your feet are still on the ground, but you're just about to leave the ground. You're moving upward already. So how much work did the floor do on you during that time? Now, to answer that question, we have to look at the point where the force was applied. So the floor is applying a force where your feet touch it, and your feet are still touching it. So we actually have that the force acted through zero distance, because delta y of the point of application and so therefore this work was actually zero. Now that's interesting because your kinetic energy increased. And so where did that energy come from? Well, it's something we haven't dealt with yet. It has to have come from, the energy came from you. You were metabolizing the Cheerios you had for breakfast this morning. And so that came from internal energy, which is something we haven't talked about yet. But the work done by the floor was actually zero. So we have to pay attention to the point at which the force was applied. Now, what do we do if the force is changing, if it's not a constant force? Well, basically what we have to do is divide. So for example, a mass on a spring. Okay, so we have a mass with a spring exerting a force on the mass, and as the mass moves, the spring stretches more or less, or is compressed more or whatever. And so what we need to do this, and I'm not going to go over it now, but there's a section, you should read section 6.6 in the book, is we simply divide the displacement up into little pieces. So if the mass goes from there to there, and now the force is smaller, maybe even in the other direction. Let's say it's even in the other direction. What we need to do is we need to divide this displacement up into little teeny delta R's, just like we divided time intervals up into little delta T's when we were applying the momentum principle, and then calculate work during each one with some average value of the force, and then sum those all up. Now, sometimes we can just make those intervals infinitesimally small, and then we get an integral that we can actually evaluate. Sometimes we get an integral that we can't evaluate, in which case we're back to doing it numerically. So that's the basic scheme here. So what happens if So right now we've been looking at up to now we've been looking at change in kinetic energy of something, change in speed. But what happens, can the rest energy of something change? What about this term? And the answer is yes. The rest energy of a system can actually change. And when the rest energy changes, then some of that rest energy can be converted to kinetic energy. And there's actually a pretty common example, although you may not really have encountered it. It turns out that a neutron is very stable when it's inside a nucleus bound to other protons and other neutrons. But when it's an isolated neutron, after about 15 minutes on average, it actually falls apart. So a neutron, which is a neutral object, goes to a proton and an electron and an antineutrino. So this is a proton, this is an electron, and this is an antineutrino. So and this is called beta decay, and it can happen even if the neutron is in a nucleus, and some radioactive elements decay via beta decay. So and what you detect, the proton pretty much stays there in the nucleus, and what you detect coming out is the electron. What's a neutrino? A neutrino is a tiny particle. It's not made of it like electrons. It's made of itself. It's a lepton. It has, you can guess from its name, it has 0 electric charge. And it's not made of quarks, so it doesn't interact very much with anything. In fact, it interacts only, it doesn't interact through the electric force because it's not charged. Its mass is very, very, very tiny. In fact, until about 15 years ago, scientists thought that neutrinos didn't have any mass. They were 0 mass objects like particles of light, like photons. But now it's been found that they have very small masses, and people are working on trying to resolve them. It's tough to do because it's hard to measure neutrinos because their interactions with matter are so rare. And there's other examples of reactions. There's fusion, which occurs in the sun. So we have fusion. So this is neutron decay. Where we have, for example, ordinary hydrogen plus deuterium, which is a hydrogen atom, a hydrogen nucleus that has 1 proton and 1 neutron, can combine to form helium-3 and a photon. I'm writing it as a gamma because it's called a gamma ray. And these things have, and some of the, so rest energy changes, identity changes, basically change of identity. When rest energy changes, the identity of the object changes. And there's fission, nuclear fission. So if we have a neutron plus uranium-235, it can decay in a variety of ways. It can make things like barium-141 and krypton, 92 and 3 more neutrons, or it could delay and decay into palladium, which is 118, I think. Okay, so there are lots of ways it can decay, but when the nucleus, the uranium nucleus, gets tickled by a neutron and falls apart like this, energy is released. So there are lots of ways in which this can happen. We can measure energies released in joules, but for a single nucleus, it's a very small number of joules. So we typically use a new energy unit called an EV, which is 1.6 times 10 to the negative 19 joules. It stands for electron volt. And it's the amount of energy, this will make sense next semester, that an electron would get if it moved through an electric potential difference of 1 volt, and that'll make difference for. So let's think about, so how do we analyze this? Well, we just apply the energy principle. There's nothing fancy about it. As I said before, and I'll say again, absolutely all energy principle problems can be solved by starting out by you just write down the energy principle in this form, and then you expand, you fill in the quantities you know, and you see if you can find the unknown. So we're going to consider neutron decay briefly. A neutron goes to a proton plus an electron plus an antineutrino. And we're going to consider that when they're very far apart. So they're born with lots of kinetic energy and they move away from each other. And in fact, momentum has to be conserved. So if we have a neutron at rest here, when we get a proton and an electron and this neutrino, their momenta, they have to be going in directions so that their momentum actually adds up to 0. So we have to choose a system and surroundings, and as in many cases, the thing to do is to choose the system that's everything. So we're going to choose system is all particles. And the surroundings, well, in this case, there's nothing significant. So we have this isolated neutron in outer space that's falling apart, and so there's nothing much. And that means that the work done is 0 because there's nothing in the surroundings affecting it. Okay. So in this situation here, and we have to choose an initial and a final state. So this is our initial state, and this is our final state, all the particles far apart. So what we want to do is start out and we want to find out what the total, the question is. So what's the question? The question is final kinetic energy of all particles. So to do that, we're going to have to, so our unknown, since it's the final kinetic energy, our unknown's going to be somewhere in here. But we just need to expand out this energy principle. So So let's consider the following question. So here's our system. Here, we'll make it bigger for a second. It's a neutron goes to a proton, an electron, and a neutrino far away from each other. And what we want to do is we want to just expand out all the terms that are in this right-hand side, the initial total energy of the system. And remember that the initial state was just the neutron. Okay, so the initial situation is just the neutron. So what terms should we have in our expression for the initial energy of the system here? K is obviously kinetic energy. Sub n means sub-neutron. Now remember, we're doing the initial energy of the system. Okay, so most of you, the majority, said that answer 2 was correct, and you are correct. And let's see why. So 2 is indeed correct. So this is correct. And the reason is that in our initial state, all we've got here is the neutron. That other stuff isn't there yet. And the neutron is a particle, and so it only can have 2 kinds of energy. It can only have its rest energy, so mc squared, and whatever kinetic energy it has initially. Okay, those other particles aren't there yet. If you said 1, then you're thinking only of kinetic energy. And in this case, since it's actually really important to include rest energy, because this thing's going to change identity and some of its rest energy is going to be transformed into kinetic energy. So that's not enough. So what's the next question I'm going to ask you? I'm going to ask you, in the final state, so is the rest, okay, so we have a question. Is the rest energy of the neutron equal to the sum of all its constituents? And the answer is a little subtle. So let's talk about the rest energy of a nucleus for a minute. Well, when we form a nucleus, a neutron, say protons and neutrons bind to each other through the strong force. And in order to do that, they actually give up some energy. So a nucleus, this bound system of protons and neutrons, the rest energy of the nucleus is actually slightly less than the energy of its constituents. So is the energy of a neutron equal to the energy of its constituents? Well, there are quarks in there, and yeah, they make up the energy of the quarks, contribute to the energy of the neutron, but we'll see that that binding, and this is true of chemical binding too. So the molecule H2 has actually slightly less rest energy than 2 hydrogen atoms would have. So here in this system, now we're interested. So the next question is, how do we write out the terms for the final energy of the system? Okay, so we decided the initial energy was, the only thing there was kinetic energy and rest energy of the neutron. Now let's think about the final state where we've got, so here's the final state, we've got the proton, the electron, and the antineutrino. And So the question is, which of these expressions correctly gives us all the terms of energy for this final state? So what we're doing here is we're listing all the terms and not worrying about their values right now. If there's zero, we'll take care of that later. But in fact, the question is, what do we have to worry about? Which terms do we have to worry about? And what most of you said was that this is in fact a set of terms that are energy terms that are important in the final state, and that's correct. So we just count we have to make sure we've accounted for all the particles. So we've got a proton. So here's the kinetic energy of the proton and the rest energy of the proton. We have an electron. So here's the kinetic energy of the electron and the rest energy of the electron. And we've got this neutrino. So here's the kinetic energy of the neutrino and the rest energy of the neutrino. Now, answer 3 isn't correct. So 2 is correct. 3 is not correct because the neutron isn't there anymore. It's gone. It fell apart. So we can't have the neutron in the final state because it no longer exists. The particle exploded and turned into other things. So the neutron is gone, and all we've got is these other particles here. So once we chose a system, we had to stick to it. And so now we've actually we're ready to write this equation out. E final equals E initial plus work done by the surroundings, which is 0. And we had here the kinetic energy of the neutron and the rest energy of the neutron. Here we have the kinetic energy of the proton and the rest energy of the proton, the kinetic energy of the electron and the rest energy of the electron, and the kinetic energy of the neutrino and the rest energy of the neutrino. So now here's our energy principle equation all written out. Okay, so let's say the neutron is initially at rest. So its kinetic energy was 0. And what are we solving for? Well, the unknown is the sum of these kinetic energies. So if we rewrite this equation, we'll find the kinetic energy of the proton plus the kinetic energy of the electron plus the kinetic energy of the neutrino plus the rest energies is equal to the original rest energy of the neutron. So if we knew the rest energies of all these things, we could figure out, so this is our unknown. Okay, well, it happens that we do actually know the rest energies of these things. So the rest energy of the neutron is actually 936.6 million mega electron volts. Okay, so 1 MeV is 10 to the 6th EV, and 1 EV is 1.6 times 10 to the negative 19 joules. The proton rest energy is sorry, that's a 939.6 MeV. The proton rest energy is actually a little bit less than that of an electron, 938.3 MeV. Here, let's, plus, so this is 938.3 MeV. The rest energy of an electron, it's much lighter, so it's 0.511 MeV. The rest energy of a neutrino is very tiny. It's on the order of 10 to the negative sixth MeV, and people are still measuring this. So about on the order of 1 EV, so we can pretty much neglect that. And so it turns out that the total kinetic energy, so we solve for, is going to be about 0.8 of a million electron volts. And this was possible because the rest energy of the neutron here was greater than the sum of the rest energies of the proton and the electron and the neutrino. So some of that rest energy got converted to kinetic energy. So so E rest went to kinetic energy. Okay. So we see that rest energy can be converted into kinetic energy. There is, however, something. Now we did this correctly because we took the final state as being these particles far away from each other, so they basically weren't interacting. But if we have a system with particles that are interacting, so interacting particles, we're going to see that we need another kind of energy. And we can actually see this from a really, really simple situation. So let's consider an incredibly simple situation. We have the Earth, and we have a ball. And the ball falls toward the Earth. Okay, so the ball starts here at some y initial, and it travels to some y final here. Okay? And obviously, as it travels, it's toward the Earth, it's going to speed up, right? So we know how to analyze this system. We can take this system just to be the ball, and then the surroundings are the Earth. And we don't have a problem, right? Because we can write E final is E initial plus work done by the surroundings. And so we will write this out. The mass of the ball, C squared plus K ball initial plus work by the surroundings is equal to the mass of the ball c squared plus k final. When we analyze this, we can get the change in kinetic energy of the Earth from the work done on it, of the ball by the work done in it by the Earth. Okay, so let's say the ball has a mass of 1 kilogram. We consider a situation in which it falls a distance of 2 meters, speeding up. So what's the work? We pick the ball as the system, the surroundings are the Earth. What's the ball? What's the work done by the Earth on the ball? Now, think about two things. Think about the relative directions of the force and the displacement. And think about the change in the kinetic energy of the ball, right? These two things are related. Okay, 2/3 of you said that the work done by the surroundings is positive 1.96 joules, and that is correct. So those of you who said it was negative are being sloppy at this point. There's two ways to make sense of this, and you need to consider both. Here's the ball, here's the force by the Earth is down. The ball moves from final to initial. From initial to final. So that's your delta R. The force and the displacement are in the same direction, so the work is going to be positive. Plus, we have numbers that we can actually use to check that. So this is 2 meters. So say this was at 10 meters and now it's at 8 meters. So delta Y is going to be 8 meters minus 10 meters. It's always final minus initial, which is a minus 2 meters. F sub Y is going to be a minus 0.1 kilogram times 9.8 newtons per kilogram. And so the work done by the Earth is going to be a positive, we're multiplying two negatives, positive 1.96 joules. Okay, you've got to get this right. So questions about this? This was fine. There was no problem. The work done was positive and the ball speeded up, right? So we had work was greater than 0. The kinetic change in kinetic energy of the system was greater than 0. So we're all fine, right? Not a problem. Now let's consider, though, we choose a different system. Let's choose the ball plus the Earth, because we can choose a system with two objects in it. So here's our falling ball. Here's the Earth. Okay, the ball goes from initial to final. The force by the Earth is down. So system, ball plus the Earth. If the ball plus the Earth is the system, what's in the surroundings? Nothing. That's right. Now there is air, and we're going to neglect, so air would be a legitimate answer. We're going to neglect air resistance here. Okay, so now I want you to be very careful and take this seriously. Take our choice of system here very seriously. We have the system is the ball plus the Earth. The surroundings, there's nothing significant in the surroundings. So what is the work done on the system by the surroundings here? So play the game. We've picked a system. It's the ball plus the Earth. So here's our system. So just apply the definitions. So the overwhelming majority said that the work done by the surroundings is 0. And that is absolutely correct because there's absolutely nothing in the surroundings. So the work done by the surroundings is indeed 0. This force acting on the ball was a force due to an object in the system, not an object in the surroundings. So the surroundings actually did no work at all on the system of ball plus Earth. Now, we have a problem. And that may have been what bothered some of you who said something else other than the work was 0. We have a problem because we have the change in energy of the system as the work done by the surroundings. This is 0, and yet the kinetic energy of the system, so it should be that the change in energy of the system should be 0. But we know that the kinetic energy of the change in kinetic energy of the system is actually greater than 0. And we know the rest energy of the Earth and the ball didn't change. So something's wrong here. It looks like we've got 0 input of energy from the surroundings leading to an increase of energy of the system. And that can't be right. So what we need is a new kind of energy. We need to increase adjust our bookkeeping so that we're actually counting this correctly. So we need a new kind of energy. And this is going to be, we're going to call it potential energy, not the greatest term, but that's what it's. And it's a property of pairs of interacting objects within a system. And the key, pairs, is really key. And so we see in this situation that the kinetic energy of the Earth ball system went up, and something has to go down to compensate because the surroundings didn't input any energy. And so this potential energy, it really should be called interaction energy. Has to have been changing. Now, how do we, so now we could write this equation legitimately. We could say that the change in kinetic energy of the system plus the change in this potential energy of the system, and it's written with a symbol U, is now equal to the work done by the surroundings. And this is potential energy, symbol capital U. And we see here that if the potential energy is a property of pairs of interacting objects within a system, we have 2 objects in our system, the ball and the Earth, so their interaction, that we have a pair of interacting objects. When we had just the ball in the system, then there was only one object in the system, and so there wasn't this interaction energy. The Earth was part of the surroundings. So in a certain sense, it's a bookkeeping thing, but it turns out to be important and powerful. So now, how do we calculate this? Well, we know the change in kinetic energy of the system, right? So the change in kinetic energy of our system, of the Earth plus ball, was plus 1.96 joules. And so it must be that the change in potential energy of the system must be a negative 1.96 joules. And that would equal 0. And we can see from this that the change in potential energy of the system is equal to the negative of the amount of work done on the ball by the Earth. So it's equal to the negative of work done by objects internal to the system. So how do we calculate this for different interactions? Well, we'd like to have a general way to do it instead of having to keep switching systems. So let's consider gravitational energy, potential energy, but let's be more general and let's use the full formalism here. So let's gravitational potential energy. So we have two objects that are attracting each other gravitationally and with equal and opposite forces. So this is object 1, that's object 2, so we'll call this F on 1 by 2 and F on 2 by 1. And these objects attracted to each other move a little closer together. So they started out there, but now they're here. So there was a distance d1 that one moved and a distance d2 that one moved. So the relative distance between them, so the work done, the internal work, if we take these things as, both of these things as the system, the internal work is just going to be F on 1 times d1 plus F on 2 times d2, but we know that these forces are equal and opposite. And we know that the displacements are both going to be parallel to the force, because that's a delta x1, 2, and that's our delta x1. And so these are both going to be positive numbers. And that makes sense because as they move together, these things are speeding up, right? So we can always do that sanity check. And so we have the same force, d1 plus d2, or this is the same as the change in the separation of the two things. So it's really the same as if one thing stayed in one place, and so this is F delta x, the change in separation. So only really the relative position matters. So we need the change in r, where r is our vector that's our friend. That's the vector that we draw from one object, the object that's the source of the force, to the object experiencing the force, so that we can calculate the gravitational force, right? So what we want to get, so the internal work, so the change in potential energy is equal to the negative of the internal work, and so that's going to be into the negative of the internal force times the displacement of these two objects. Now, if we do this in one dimension, it's kind of easier to see. It works in, so delta U is going to be minus Fx delta x here, or we can just rearrange this to get delta U over delta x is the negative of the x component of the force. And so we can write that in as a derivative. Du dx is minus f sub x, etc. Du dy is minus f sub y. And this particular kind of a derivative is actually called a spatial derivative, is called a gradient. So basically, to find an expression for potential energy, all we need to do is use this calculus formalism we've come up with. So if the force is the negative gradient of the potential energy, then we know that we have a minus gm of one object and mass of 2 over r squared is equal to minus du dr. And so the question is, what is u as a function of r? And so what we have to do is take an antiderivative. So for those of you who are just taking calculus, we're going to take an antiderivative, just differentiate backwards, see what we'd have to differentiate to get this force. And, or it's an indefinite integral if you've gone a little further. So the question is, we can, so what would we differentiate to get this? Well, so we can write the gravitational force as a minus gmm r to the minus 2, right? And that helps us think about it a little bit. And what would we differentiate to get r to the minus 2? Well, it's going to be r to the minus 1, because ddr of r to the minus 1 is going to be a minus 1 times r to the minus 2. So, so it looks like a change in gravitational potential energy is going to be equal to, so our gravitational potential energy is going to be equal to, let's say U gravitational is equal to a minus G M M over R. Now, let's make sure the signs come out right. If we differentiate that, we want the negative derivatives. So we want check of G of minus GMM over R is going to give us a minus GMM over a minus R to the minus 2, which gives us a minus GMM over R squared. So we've got an expression for gravitational potential energy as a function of separation. So really it's U gravitational as a function of R. Now notice that that's a negative quantity. So G is positive, M is positive, M is positive, R is positive, separation. So this is, it's less than 0. That's okay. It's fine for it to be negative. So let's think about what a graph of this would actually look like as a function of position. So which of these things is actually a graph of gravitational potential energy of two interacting objects as a function of their separation? So here's the function. So it's this function. So which of these is a graph of that function? Okay, and for once, the majority is not correct. So most of you said 2, which is wrong. And only about a third of you said 1, which is correct. So let's see why. So first of all, let's just look at this expression. So U is minus GMM over R squared. Okay, so G is a positive number. The mass of something is a positive number. The distance between two things is a positive number. So all of those quantities are positive, and the negative sign must mean that this quantity is going to always be less than 0. So that means it can't be 2, which is greater than 0, and it can't be 4, which is greater than 0. Now, if R is a very small number, you're dividing a positive number by a very small number, so you're going to get a big number. So this is a graph of something times plus 1 over R, because as R gets very small, you're dividing by a small number, it gets big. But this is a graph of minus 1 over R, because as R gets big, it gets large and negative. I mean, as R gets small, U gets large and negative, and as R gets big, U goes to 0. R squared is the gravitational, whoops, sorry, it's R. So the force, if we were plotting the gravitational force, that indeed is a minus GMM over R squared R hat, right? But this potential energy, this scalar, which was the thing that you differentiate to get the force, is actually 1 over R. And so this is just a linear graph. That can't be right. That's a constant. That doesn't change. So definitely this is the right answer. So how would we use this? Well, if we have a rock falling toward an asteroid, see, the mass of the rock is 8 kilograms. It's initially 100 kilometers away with speed 5 meters per second. And what's the speed? The radius of the asteroid is 10 kilometers, and its mass is 2 times 10 to the 16 kilograms. So what is V final just before it crashes onto the surface? So here's our asteroid. Here's the rock falling toward it. It starts out with the initial, but just before it hits, it's got some speed V final, and we want to figure out what it is. Well, we just use the energy principle. Your final is E initial plus work. We choose the system as the rock plus asteroid. So the surroundings, really there is nothing significant. So work is 0. And so now we have to do the same thing we always do, which is to write out all the terms. So we have the final kinetic energy of the rock plus the final kinetic energy of the asteroid plus the rest energy of the rock plus the rest energy of the asteroid is equal to the initial kinetic energy of the rock and the initial kinetic energy of the asteroid plus the rest energy of the rock and the rest energy of the asteroid. Now, some of these things don't change. Nothing's changing identity here, so those go away. We note that the asteroid is much more massive than the rock, so for all intents and purposes, we have the kinetic energy of the asteroid is going to, the change in kinetic energy of the asteroid is 0. But what else has to go into this equation? What else do we need to add to this equation? We need to add the potential energy. So the U final of the asteroid rock system here. And here we need the U initial of the asteroid rock system. And so what we're going to end up with here is going to be, we can now write this out. So this is going to be a minus G mass of the asteroid, mass of the rock, over the final radius, plus a half mass of the rock, V final squared, is going to be equal to minus G times the mass of the asteroid, mass of the rock, over the initial separation, plus a half mass of the rock, V initial squared. Yeah, Hunter was right. I made a mistake in that equation. So now we can plug in. So where's our unknown? Where's Waldo here? So here's our unknown. And do we know the rest of the quantities? Well, we know the radius of the asteroid, so that's just how far it is. We know the mass of the asteroid, we know the mass of the rock, we know G, we know the initial speed, so we can actually solve for this quantity. And if you want to work it out yourself, we get a V final is equal to 16.3 meters per second. Okay. So there are examples in the text to study. You should definitely do this. You should read the section on work due to changing forces.